All right, hello and welcome to lecture on, what is it? It is the second to last Monday in September. Hopefully all is going well. I was looking a little bit at, just a little bit at Canvas today before class, and I don't have hard and fast numbers, but I saw that most of you still have the exam to take. So that again is a reminder that closes tonight at at midnight. Well, technically at 11:59 p.m. Also. If anybody is struggling with the calculations for the lab, totally hit up office hours tonight. We have office hours from 7 to 10. I do need to put a caveat that in the middle of office hours, I have to pick up my kids from a thing at 9. So I'll be stepping out of office hours around like 8:55, and I'll be back about It's only like 5 minutes away from our house. I'll be back in like 15 to 20 minutes, but I'll write a note on my screen letting everybody know when I am AFK, and then also when I'm back, and I'll stay an additional length of time, so you won't be losing out on any office hours time. But if you roll in with a question and it's like 9:05 and you're like, why does it say AFK? It's gotta pick up my kids. My wife's working a night shift tonight, so I'm juggling doing work and all of the dad stuff because I work from home. She works at the hospital. So, anyways, well, it's weird. I work from home now. Now that I'm streaming. Okay, the end of last lecture was a bit of a debacle. We lost audio. Also, my Surface stopped responding to its stylus, so it looks like when I'm writing with my finger, I look like I have the handwriting of a 6-year-old. But everything's back. I troubleshot the system over the weekend, and we're all good to go. So again, just a reminder. So we're picking up with the example that I left you with on Wednesday of last week. And so just as a reminder, here is what we are dealing with. We're told that HBr reacts with sodium carbonate to produce sodium bromide, carbon dioxide, and water. And I asked you to do 3 things. First, to write a balanced chemical equation. Second, to determine the theoretical yield of carbon dioxide in grams. If you mix 1.00 gram of each reactant, and then C, I told you that the actual yield is 0.265 grams of CO2. And I ask you to find the percent yield. All right, so this is a fairly typical stoichiometry problem. You'll definitely see something like this on the second exam 2. This is the type of stuff that will be our bread and butter moving forward. It's stoichiometry, it's limiting reactant, it's balancing chemical equations, it's naming, right? It's nomenclature, it's theoretical yield, it's percent yield. So this is the stuff that you learn in the first semester of Gen Chem. So let's first talk about balancing our chemical equation. All right. So we're told that we have HBr reacting with sodium carbonate. Now, sodium is a cation that we can figure out its charge from the periodic table. It has a charge of +1. Carbonate is an anion whose equation is CO3 and whose charge is -2. So we're going to need two positive sodium cations to balance with our negative carbonate anion. So this will be Na2CO3. All right. So those are our two products, our two reactants, and our products are sodium bromide. Now we know what sodium is, the sodium cation. Bromide, which we determined that charge from the periodic table as well, is -1. So sodium and bromide combine in a 1-to-1 ratio. So this will be NaBr plus carbon dioxide. This is a covalent compound that has 1 carbon and 2 oxygen, and water, which is H2O. All right. Now, this is not our balanced chemical equation. We've simply written out the reactants and products. Next, we have to take a chemical inventory, an atomic inventory, to see if it's balanced and to figure out how to balance it. So we have hydrogen, bromine, sodium, and carbon on both sides of this equation. And on the reactant side, we have 1 hydrogen, 1 bromine, 2 sodium, 1 carbon, and 3 oxygen. On the product side, we have 2 hydrogen, 1 bromine, 1 sodium, 1 carbon, and then 2 oxygen from CO2, plus 1 oxygen from water. All right. Now we need to balance this chemical equation. And so when I look to see what's unbalanced, the first thing that jumps out to me is hydrogen. I've got 2 on the product side, 1 on the reactant side. So the only way to balance hydrogen is to multiply HBr by 2. This balances hydrogen, but ruins bromine, which was totally happy, right? We had 1 on each side, but now we have 2 on our reactant side. So now we have to go back, to the product side and balance bromine. The only way to get 2 bromines on our product side is to multiply sodium bromide by 2, and you'll notice that the act of balancing our number of bromine atoms also balances our sodium atoms. So this is our balanced chemical equation for the reaction between HBr, which is hydrobromic acid, and sodium carbonates. All right. Now, part A, locked and loaded in the can. Part B, we need to determine the theoretical yield of CO2 in grams. So we're asked to find how many grams of CO2 if we start with 1.00 grams of each reactant. All right. Now, we went over this in last lecture. Anytime you're given starting amounts of more than 1 reactant, we have to do a limiting reagent calculation. we need to figure out which one is going to run out first, because whichever one runs out first will determine the amount of product we produce. And so we calculate how much we could theoretically produce from either reactant, and then we calculate how much CO2 would be produced. Then whichever number is smaller, that comes from the limiting reactant, and so that quantity will be our theoretical yield. So starting with HBr, we have 1.00 grams. All right. Now, looking up the oh man, heart attack, chemistry textbook almost fell. Always a good time. That's why you shouldn't put it on the edge of the table. So bromine has a so calculating our molecular weight here. Bromine has an atomic mass of 79.90, and hydrogen is 1.008. When you add these together, you get 80.908. Now, using the two numbers that I just did, our last significant digit would be in the second decimal place, and we need to keep that in mind as we move forward. So we can use this to convert from grams of HBr to moles of HBr, because that ratio is 80.908. Again, this number only has 4 sig figs. 80.908 grams of HBr are in 1 mole. So grams of HBr cancels. Now we're in moles. All right. Converting now from moles of HBr to moles of CO2. This ratio we get from our balanced chemical equation, where we see that 2 moles of HBr produce 1 mole of CO2, and now moles of HBr cancel. Finally, we need to convert from moles of carbon dioxide to grams of carbon dioxide, and to do that, we need a balanced molecular mass for CO2. Carbon has an atomic mass of 12.001. Oxygen has an atomic mass of 16.00, which we multiply by 2 because there are 2 oxygens in 1 molecule of carbon dioxide. So this comes out to be 44.01 grams of CO2 in 1 mole. Moles of CO2 cancel. All right, and now we're ready to crunch our numbers. So we have 1 divided by 80.908. Whoops. 80.908. There we go. Divided by 2 times 44.01. Let's see. We are limited to 3 sig figs, because our initial mass has 3 and everything else that we use has 4. So we got to roll with the fewest. So this will be 0.272 grams of CO2. All right, and so that is our, that's how much carbon dioxide could be produced with 1 gram of HBr, but we don't know if that's our theoretical yield, because we don't know if HBr is our limiting reactant. To find that out, we need to perform this exact same calculation with 1 gram of sodium carbonate. All right, so we have another molecular mass to calculate. Sorry, there are 3 oxygens. in sodium carbonate. So sodium has an atomic mass of 22.99, carbon 12.01, oxygen 16.00, and here we have we have 3 oxygens and 2 sodium in the mix. Right, so 22.99 times 2 plus 12.01 plus 48 comes out to be 105.99. You'll notice with sig figs that this number is fine because its last significant digit has the same precision as all of these masses. They all have the same precision. So no need to round or anything. So we have 105.99 grams of sodium carbonate. Under 1 mole. So this should be Na2. And these cancel. Next, we can convert from moles of sodium carbonate to moles of carbon dioxide. And here the ratio is a 1-to-1 ratio. 1 mole of sodium carbonate produces 1 mole of CO2. And then our final, these cancel. Our final unit conversion, we use the molecular mass of carbon dioxide that we calculated above. To convert from moles of CO2 to grams. Now these cancel. We're left with grams, and we can crunch our numbers. So we have 1 divided by 105.99 times 44.01 comes out to be 0.415 grams of CO2. And comparing these two, we select the smaller of the two as our theoretical yield. All right, this is our theoretical. And if we had been asked, HBr is our limiting reagent. It is the one that runs out first. It limits the amount of product we produce in this chemical reaction. All right, so we have determined the theoretical yield for carbon dioxide. We are ready to go on and calculate our percent yield. All right, our percent yield is equal to, this is an equation, we talked about it last week. It's equal to actual yield over theoretical times 100. And we were told, actually, the actual yield of CO2 was 0.265 grams. We just calculated our theoretical yield as 0.272 grams. So you'll notice that our masses cancel. .265 divided by 0.272 times 100 comes out to be 97.426 7. But the we're limited to 3 sig figs. So we count off the first 3, and our final answer will be 97.4, again, because this 2 rounds down, %. So this would be a high-yielding reaction, clocking in at 97% yield. All right. So this problem really encompasses everything we've learned so far. It is an all-encompassing stoichiometry problem. It has theoretical yield, % yield, limiting reactant, the whole shebang. All right. Now, so moving on, and again, as a reminder, we have been, this is chapter 4, and we are talking about solution phase chemistry, and this brings to conclusion our review of stoichiometry, right? You're going to be encountering stoichiometry, doing stoichiometry for the rest of this course, and so I wanted to go over it to make sure that if you're a little rusty from your pre-req course, you have an idea of what's going to be coming at you, not just on exam 2, but exam 3, etc., and of course the final. But now that we've covered stoichiometry, we're ready to transition into a discussion of the solution phase. All right. Now the solution phase. So it'd be good to talk about what is a solution, because a solution in chemistry is very different than a solution in mathematics. A solution in chemistry is a solute dissolved in a solvent. All right. A solution is a solute dissolved in a solvent. Now, this is sugar into coffee, right? This is when you pour sugar into coffee. The sugar is the solute, the coffee is the solvent, right? When you pour cream into coffee, the cream is the solute, the coffee is the solvent. So when you crack open a carbonated beverage, as I have here, right? The bubbles that come out of this are a gaseous solute that was dissolved in solution under high pressure. Now they're escaping, but the gas has been dissolved in a liquid. The gas solute has been dissolved in a liquid solvent. All right. So the solute, the thing that dissolves, the solvent is the thing that does the dissolving, and solute plus solvent equals solution. All right. Now the thing with solution is you can have different concentrations for your solution. So, for example, if you were to taste the amount of sugar that for example, that I put in my coffee, I actually don't put any sugar in my coffee, so if you taste it, that would be a concentration of 0. Versus the amount of sugar that my mom puts in her coffee. My mom puts so much sugar in her coffee that you could pour it over pancakes and use it as syrup, right? The concentration is very high for my mom. For me, the concentration is very low, and concentrations come in all shapes and sizes. There are many different types of concentration units. And we'll be covering several of them over the course of this semester. But they all have this in common. They always boil down to the quantity, some quantity of solute some quantity of solute over the ratio, some quantity of solution or solvent. And depending upon the unit, sometimes it's a quantity of just the solvent alone, sometimes it's a quantity of the solution, everything together. But it's always one or the other. It's some ratio between the quantity of solute to solution or the quantity of solute to solvent. All right. Now, the concentration unit that I'm going to take some time to talk about right now, and far and away, at least from a chemistry perspective, the most important type of concentration unit is known as molarity. Okay, hang on one second. Actually, before I start writing about molarity, I see we've got a question in the comments. What if CO2 was on the reactant side and it asks you to find CO2 reactant side? Is that possible? Okay, Cameron, great question. Cameron, so I started typing and then I realized, wait, this is going to be a really, really long text, but it'll be a shorter verbal answer. There are two ways in which a product could be asked about. Sorry, two ways in which a reactant could be asked about. One, you could be asked how much reactant is consumed. All right, so you're given a starting quantity of one reactant, you're asked how much of this other reactant gets consumed in this reaction. The second way is, we've talked about the limiting reagent, but for every limiting reagent, there's an excess reagent. The other reactant in the reaction, there's leftover material from that didn't get consumed, right? And so, another question that could be asked is calculate the amount of excess reagent left over after the reaction. And I'm totally down to do that, but let's save it for office hours because it'll derail the course of lecture right now. But hit me up in office hours, or if you can't make it to office hours, shoot me an email and say Chem 400 office hours in the title, and I will go over that later tonight, how you would do that calculation. So that is a excellent question. And we will go over that in further detail during our office hours. All right. So let's talk about molarity. Molarity is abbreviated with a capital M, and the molarity of a solution is equal to the moles of solute over the liters of solution. All right, it's defined as moles of solute over liters of solution. So that is the definition of molarity. That is how you calculate it. Now, one thing to note, so you have molarity, which is equal to, yeah, dude, absolutely, moles over liters. Notice that there are, in this equation, 3 variables. All right, we have three variables in this situation, which means, this is the important thing, given two of them, given two, you can always find the third. All right? And more likely than not, you'll often be given the molarity of a solution and the volume of the solution, which allow you to find the moles, which allow you to do stoichiometry. All right, so you'll see applications like that time and time again in the context over the duration of this course. All right. One thing that we should mention, because this comes in quite a bit with lab, is when you're dealing with solutions. One thing that's quite common to do and a very common calculation to be asked to do both for lab or for in a lecture testing context is something called dilutions. All right, dilutions. What happens in a when you do a dilution is it's simply adding solvent to a solution which decreases the concentration. All right. If the concentration, and if we look at molarity, is equal to moles of solute over liters of solution, notice that we're adding solvent. So we're increasing our denominator. And when you increase your denominator, what happens to molarity? It drops, right? Whoa, holy moly. What happened there? There we go. When you increase your denominator, what the heck? Hang on. There we go. Okay. Sorry, Photoshop's spazzing out a little bit. When you increase your denominator, you decrease the overall value, right? The molarity. So that's what you're doing in a dilution experiment. You're adding solvent to a solution to decrease the concentration. Here's why this is important. Often, when our stockroom goes to purchase a chemical, which we haven't had to do for a little while, right, with all the COVID stuff, but when it does, it'll often the stockroom humans will often purchase the solution at a very high concentration. For example, we buy 11.65 molar hydrochloric acid on the reg. That's the standard molarity in which you buy it. But this concentration is way too high for the needs of most experiments. Most experiments need solutions of HCl that are between maybe 0.1 molar to 6 molar at the highest, but most of them usually use solutions of HCl that are like 0.1 to 3 molar. But we have this stuff in the back room, in the stock room. How do you make a solution of HCl at the appropriate concentration. Let's say that we need 500.0 milliliters of a 2.0 molar solution of HCl. The question would be, how much 11.65 molar HCl should be used? And the way you solve this problem is with something called the dilution equation. All right, the dilution equation is the initial molarity or concentration times the initial volume is equal to the final molarity times the final volume. And one thing you'll notice is that we know what our final volume should be, right? We want to make 500 milliliters. We also know what our final molarity should be. We want a 2.0 molar solution. And we know what molarity we're starting with, right? We're starting with 11.65 molar HCl. So this allows us to solve for the initial volume, the amount of 11.65 molar HCl that we need, if we just divide both sides of this equation by our initial molarity. All right, so it rearranges, and we get initial volume is equal to final molarity times final volume over initial molarity. And we know these three numbers, right? Our final molarity is 2.0 molar. Final volume is 500.0 milliliters. Our initial molarity is 11.65. Molar. And now we're ready to crunch the numbers. You'll notice that molarity cancels with molarity. We're left with a volume unit of milliliters, which is good, right? Because we're solving for volume. So now we can crunch our numbers. 2 times 500 divided by 11.65. All right, my initial volume. So my calculator is telling me that the correct value is 85.83690099. But sig figs wise, I can only keep 2 because my final molarity only has 2 sig figs. So I count my first 2 off. 8 will round up. So the initial volume of 11.65 molar HCl that I need is 86 milliliters. This is the correct answer with the correct units and the correct number of sig figs. All right, so that is how you use the dilution equation. Again, just because I want to just explicitly write it out separate from anything else. This is called the dilution equation. Which is 11.65. No, it's not. Holy moly. That's the concentration of HCl I was just using. Sorry about that. The dilution equation is initial molarity times initial volume equals final molarity times the final volume. All right. So that is the dilution equation. I just showed you how to use it, and you can find more practice in the Tro homework that is assigned but not graded. All right. Now, let's pause for a minute and let's take a minute to apply the concepts that we just learned to the stoichiometry that we just finished reviewing. Let's do the following example together. So, consider the following reaction. Phosphoric acid, which again, we'll be talking about how to name acids soon enough. Oh, let's see, question. Bailey, great question. So Bailey just asked, when using the dilution equation, does the volume have to be converted to liters to solve it? And all right, and the answer is the volume units do not need to be converted as long as they're the same. So if both volume units being used are milliliters, they'll cancel. If they're both liters, they'll be canceled. But if they're different, if one's in liters and one's in milliliters, for example, then you got to convert them. But as long as the two volume units you use are the same, you don't need to change them. And as is the example with the previous problem, we only had one volume unit, and so our answer came out just fine. Again, it wouldn't be wrong to convert it to liters. It would just be the correct answer in a different unit. Okay, Will, you've got a question. Kind of off topic, but are we going to be able to look at our... okay. So, Will, here's the thing, is it states in the syllabus that you'll not be able to see the explicit answers to your problems for your exam. We have to do that for exam security reasons. However, after the exam closes, I'm going to go through and find the problems that, as a class, you all struggled with the most, or the ones that got the poorest scores on. And I'm going to be kind of putting together that information as kind of a guide to, okay, here's what was hard for everybody as a class, so here's some guidelines, and these are the things you want to study. Now you may be thinking, well, wait a minute, the prereq exam already closed. It hasn't closed yet for the last batch of late adds. So there were people who added even, there are students who were added to other lab sections, even beyond the normal cutoff. And so I had to reopen the exam so those students could take it, just to be fair to everybody. And so that's why I haven't posted about it, because all the results aren't in. But that closes tonight, as well as exam 1, so the class will be getting kind of a double-barreled release of information, both on the prereq exam and exam 1. So you'll know what to go over, what to review, what to study, kind of as a whole. All right, so let's get back to this stoichiometry example. So we have phosphoric acid, and again, we'll talk about naming acids in our near future. This reacts with aqueous KOH, potassium hydroxide, to produce liquid water. Yeah, man, you are welcome. Liquid water and potassium phosphate, which is also aqueous. You'll notice we have phase symbols going on up in this situation. That is not an accident. So part A, as you might expect, is write a balanced chemical equation. Part B, for this problem, is determine the theoretical yield in grams of water if 125 milliliters of 2.0 molar potassium hydroxide reacts with excess phosphoric acid. All right, so let's take this one step at a time. First, let's balance our chemical equation. All right, so we need to take an inventory of the atoms on either side of our reaction: hydrogen, phosphorus, oxygen, and potassium. Hydrogen, we have 3 coming from phosphoric acid plus 1 coming from KOH. We have 1 phosphorus. We have 4 oxygen coming from phosphoric acid, and we have 1 coming from KOH and then 1 potassium. On our product side, we have 2 hydrogen, 1 phosphorus, 1 oxygen coming from water plus 4 from potassium phosphate, and 3 potassium. All right, so the first thing that jumps out at me here is potassium seems pretty easy to balance, right? We have 3 on the product side, only 1 on the reactant side, so we just need to multiply KOH by 3. This will balance our potassium, change our oxygen, and change our hydrogen. So now we have 3 plus 3, or 6 hydrogen. We have 4 plus 3, or 7 oxygen, and we have 3 potassium. So potassium is balanced. Now, hydrogen and oxygen are both a little out of whack. Oxygen, I don't know how many times 5 goes into 7, but I do know how many times 2 goes into 6, right? It goes into 6 3 times. So to balance water, we got to multiply H2O by 3, and you'll notice that in one fell swoop, we actually balance both hydrogen and oxygen at the same time. So this is our balanced chemical equation, the one we'll use in the stoichiometric calculation that we're about to do. Sorry, this had a 3, this had a 3. There's our balanced chemical equation. Now we're told here, this is not a limiting reactant problem, though it could have been. We're told that we have 2.0 molar KOH, and we're told that we have 125 milliliters of it. And we're asked to find our theoretical yield in grams of water. All right. Now here's the thing. If I had given you the mass of KOH and asked you to do this, you could have done it in a heartbeat, right? You'd have taken that mass, converted it to moles, and then taken the mole to mole ratio, KOH to water, to find moles of water, convert it to grams. But this is weird. I gave you a volume and a concentration. Here's the thing. Whenever you're given molarity and your volume, this is a one-way ticket to moles. All right? Here's how. we know that molarity is equal to moles over liters, right? So if you multiply both sides of this equation by the denominator here, liters cancel, and you get an equation for moles of solute. Moles of solute is equal to the molarity of the solution times the volume in liters. And we have molarity, and we kinda have liters. We actually have milliliters right now, right? So we need to do a unit conversion, but once we do, then we'll know our moles. So let's actually convert 125 milliliters to liters. Put mils in the denominator, liters in the numerator. 1 milliliter is, oh, I didn't leave myself any space. Let's try that again. 1 milliliter is 10 to the negative third liters. All right, here milliliters cancel. And this comes out to be 0.125 liters. All right, that is our volume. Okay. Now that we know our volume in liters, we can find our moles of KOH, and then we're off to the stoichiometric races. Now, one thing, you may want to write 2.0 molar, like so, but when I'm doing math with it, I actually prefer to write out what molarity actually is. The thing is, when I'm looking at a capital M, it's easy for me to forget what that quantity has a denominator, right? Molarity is moles of solute, which is KOH in this instance, over liters, all right? And I find for calculations purposes that it helps me a lot more, and I make fewer mistakes when I break up that big capital M into moles over liters. Now, when I multiply this by 0.125, or my volume in liters, I can clearly see that the denominator here cancels the volume unit here, and I'm just left with moles of KOH. In this problem, I'm not after moles of KOH. I want to know what my theoretical yield of water is. So next, I'm going to use a mole-to-mole ratio to convert from potassium hydroxide to water, and I can see that 3 moles of potassium hydroxide produce 3 moles of H2O, and now moles of KOH cancels. Finally, put moles of water in the denominator and grams of water in the numerator. The molecular mass for water is 18.016, 4 sig figs. Now moles of water cancel. I'm ready to crunch my numbers. So I've got 2 times 0.125 times 3 divided by 3 times 18.016. All right, so my value that I'm getting is 4.504. Sig figs wise, I can only keep 2, right? My molecular weight has 4. My volume has 3, but my concentration only has 2, so I can only keep 2. And 0 is going to round down. So my final answer then, the correct value is 4.5. Correct value, correct sig figs. And then my units are grams of H2O. All right, and that is my theoretical yield of water if I react 125 milliliters of 2.0 molar KOH with excess phosphoric acid. All right, now this is just to give you a taste, a sample of how molarity integrates with stoichiometry, but you can do this with any stoichiometry problem. And here on out in the future, you'll see molarity included in limiting reactant problems, in percent yield problems, all that stuff is applicable as long as, we should make this, belabor this point, as long as molarity is applicable, as long as you're in the solution phase, as long as you're in the aqueous phase, then you can have a concentration. If you're a solid or a liquid, that does not apply, and we're going to save gases for later. They're their own thing. Okay, let's see, how are we doing? We're doing excellent. So, now that we have been, we've been kind of introduced to different concentration units, and well, not different ones. We've only talked about one, molarity. But we've kind of got that concept under our belt. We've been introduced to it. We're ready to actually start talking about different types of chemical reactions. All right, and the first reaction class that we're going to discuss is precipitation reactions. Before we can do that, we need to introduce the concept of what it means to be an electrolyte. All right, so let's spend a minute talking about electrolytes. Electrolytes. Okay. So, first off, what is an electrolyte? All right. What is the definition of an electrolyte? An electrolyte is a chemical that forms ions when dissolved in water. Right? It's simply a chemical that forms ions when dissolved in water. So, for example, sodium chloride, if you take solid sodium chloride and dissolve it in water, this is an electrolyte. And what happens is, when you dissolve sodium chloride in water, is the process of being dissolved breaks up the ionic compound into a separated cation and anion pair. Sodium and the chloride don't remain associated when dissolved in water. They kind of split up and float apart, and that's what makes it an electrolyte, because you took this solid ionic compound and it formed ions when dissolved in water. So this would be an electrolyte right here. An example of a non-electrolyte, would be glucose. When you take a molecule of glucose, which is sugar, in the solid state. Sorry, that low key looks like the gas state to me. And you dissolved in water, the only thing that changes, sorry, this should be 6. The only thing that changes is the phase. All right, glucose goes from being a solid to being in the aqueous phase, but nothing changes. It doesn't form any ions, so this is what we would call a non-electrolyte. All right, so electrolytes form ions, non-electrolytes do not. All right. Now, this may lead you to think that electrolytes are always ionic compounds, but that is not necessarily the case. Acids actually form ions when you dissolve them in water. The difference is with an ion, the anion and cation separate. With an acid, it actually reacts with water to produce 2 ionic products, but it still forms ions when dissolved in water. So they're not always ionic compounds, and as we'll learn, not all ionic compounds are water soluble. Some are, some aren't, and we'll learn this when we get to the solubility rules. Okay, now electrolytes come in 2 flavors. All right, electrolytes come in 2 flavors. There are what we call strong electrolytes, and then there are what we call weak electrolytes. So, for example, an example of a strong electrolyte would be potassium iodide. All right, when you dissolve Ki, potassium iodide, in water, it will separate into its individual cation and anion, potassium and iodide. And when you dissolve this in water, 98% of it dissociates into separate ions. Only 2% remains associated. All right, so this is what we would call a strong electrolyte. All right, because most of the overwhelming majority dissociates. An example of a weak electrolyte would be acetic acid, whose structure looks like this. So this is a liquid. When acetic acid dissolves in water, some of it ionizes into acetate and hydronium. All right, but only 1% will dissociate. 99% of all of the acetic acid molecules remain associated and do not form ions. But because some of them do, we still call it an electrolyte, but this is what is known as a weak electrolyte. All right, a weak electrolyte. So a weak electrolyte is some dissociation, so it still is an electrolyte, but not much. A strong electrolyte is almost complete dissociation. All right, now you may be wondering, okay, well, how will we know? And for this course, and you'll get into the nuances of this topic in Chem 401, and I can't wait for you to get there. It's awesome. For now, we're going to take a more simplistic view. All right, so if you have when you have aqueous ionic compounds, so for aqueous ionic compounds, you're going to assume they are strong electrolytes. All right. For aqueous ionic compounds, you assume they're strong electrolytes. For solid ionic compounds, you're going to assume that these are non-electrolytes. All right, and so that is the assumptions that we're going to be operating on in Chem 400. Again, you'll get to something called the solubility product in Chem 401, and you'll learn all the nuanced details, that nothing is completely insoluble and nothing is totally soluble. It's all on a continuum, and you'll get to break that down. It'll be wonderful. But for now, we're going to assume a simplistic view of the universe. Whenever you see aqueous for an ionic compound, assume that it's completely dissociated. And whenever you see solid for an ionic compound, you assume it's completely associated, all right? Okay. That being said, I want to do an example here. Determine determine the molarity of aluminum cations and chloride anions in a 0.25 molar solution of aqueous aluminum chloride. All right. So here you'll notice we're being asked to determine the individual molarity of the cation by itself and the anion by itself in a 0.25 molar solution of aluminum chloride. All right. Now to solve this problem, there's one critical piece of information that you need. You need to be able to write out the dissociation of aluminum chloride. All right? So aluminum chloride breaks up into, because it's aqueous, it's an ionic compound that's aqueous, we're assuming a full dissociation, complete dissociation. So it separates into aqueous aluminum cations plus 3 aqueous chloride anions. And it's super important to pay attention here to the stoichiometry. We only have one aluminum cation, so there's only one Al3 plus floating around in solution. We have 3 chlorides, so that means we need 3 in aluminum chloride. So we need 3 free floating chloride anions in solution. Now, you may still be looking at this and going, okay, well that's interesting, Josh, but I still have no idea how to solve this. Remember the trick that I told you earlier. Whenever you're working a problem, it will be a lot easier for you to find the answer that you're looking for if you write out your molarity with its numerator and denominator separated, right? 0.25 molar aluminum chloride is 0.25 moles of aluminum chloride over liters, right? Now, notice, you're trying to find both the molarity of aluminum and the molarity of chloride, and that's moles per liter. We have liter in the denominator already, right? So we don't want to mess with the denominator. We just need to change our numerator. So if only there was a way where we knew how many moles of aluminum corresponded to how many moles of aluminum chloride. And here's the cool thing. That comes from the balanced chemical equation. You just wrote the dissociation. This shows us that 1 mole of aluminum chloride produces 1 mole of aluminum. So moles of aluminum cancel. And we get 0.25 moles of aluminum cation per liter, i.e. 0.25 molar is the concentration of aluminum cations. Let's do the same thing to find the concentration of chloride. Again, we want to leave our denominator alone, right? Denominator gets left alone. We want to cancel moles of aluminum chloride. We want to be left with just simply moles of Cl minus moles of chloride. And this ratio is a 1 to 3. 1 mole of aluminum chloride produces 3 moles of chloride anions. All right. And now we can crunch our numbers. So our molarity of chloride anions will actually be 0.75. Right, so this will be 0.75 molar, a 0.75 molar solution of chloride anions. All right, so when it comes down, so often, here's the point of what we just did. All right, often the concentration will be given for the entire ionic compound, but the individual concentrations of the cation and anion may be different. They may not be different. You can see in this example that the concentration of aluminum was equal to the concentration of aluminum chloride, whereas the concentration of chloride anions was triple the concentration of the total ionic compound. All right, so this is just something to keep in mind, something to watch for as you're doing these problems, that if you're asked to find the concentration of an isolated anion or cation, to do so, you need to convert from your molarity of the total compound to the molarity of the individual anion or cation, and you use this dissociation equation, which you'll have to write out and provide for yourself, to find what those molar ratios are. All right? Okay. All right, so we have 15 minutes left in this lecture, and we have finally come up to our first class of chemical reactions. So we are going to introduce a precipitation reaction, or introduce precipitation reactions. In our last 15 minutes here, and then we will pick up with this topic on Wednesday. All right, so let's talk about precipitation reactions. All right, a precipitation reaction occurs when two aqueous reactants combine. I shouldn't say combine. Actually, two aqueous reactants form at least one insoluble salt. All right, one insoluble salt. First, something to keep in mind, whenever a chemist says salt, we're not necessarily talking about sodium chloride. Salt is just a term that we use for any ionic compound. All right, any ionic compound can be referred to as a salt. Second, a precipitation reaction follows the following format. So first, you have your first cation, which I'm going to call cation 1, that's paired with anion 1, and these two together are aqueous, plus you have cation 2, which is paired up with anion 2, and these two are aqueous as well. Sorry, this is anion 2. All right, what happens in a precipitation reaction is the cation and anion partners swap. All right, they swap places. So the first cation gets paired with the second anion, and the second cation gets paired with the first anion. Oh my goodness, hang on. There we go. So cation 1 grabs anion 2, cation 2 grabs anion 1, and the products of the precipitation reaction are cation 1 with anion 2 plus cation 2 with anion 1. And the phases here, I'm going to put question marks. So here's the deal. If one or both of these phases are solid, then a precipitation reaction has occurred. All right, if one or both are solid, the products, if one or both are solids, then a precipitation reaction has occurred. The solid product, is called the precipitate. And this is abbreviated the precipitate is abbreviated PPT. All right, so whenever you see PPT, that's just shorthand for precipitate. All right, now this is kind of hard to see, so I'm going to give you a hard and fast example of an actual precipitation reaction. All right, so for example, the reaction between aqueous lead 2 nitrate and potassium iodide is a precipitation reaction. The products here are potassium nitrate, and lead 2 iodide. All right, and you'll notice that your first cation, lead, pairs up with your second anion, iodide, and that your second cation, potassium, pairs up with your first anion, nitrate. So it's a precipitation reaction, right? Lead grabbed iodide, potassium grabbed nitrate. And so that's part of what makes it a precipitation reaction, but you also have a solid product. So lead to iodide is the precipitate in this reaction. All right, so this is a nuts and bolts, an actual example of kind of the generic thing that I wrote on the previous page with first cation, second cation, first anion, second anion. This is a kind of a brass tacks example of what I was talking about. All right, and I have a lot more to say about precipitation reactions. We've introduced what they are. We'll dig into how to identify them, how to predict them, all that good stuff in lecture on Wednesday. Again, I'm going to be streaming tonight at 7 to 10 for office hours. If you have questions, stop by. I can't answer questions about the exam, but I can answer questions about Experiment 1, which is coming due tonight as well. And also, just as a reminder, I will be, I have to pick up my kids from a thing at 9. So I'll write on the screen when I'm away from keyboard, but note that I'll be back within 15 minutes. And I will extend the end of office hours, so you won't get gypped out of any time. All right? Okay. I will catch some of you later, and the rest of you on Wednesday. Have an awesome Monday if I don't see or hear from you before then.